but we'll briefly just look over the structure of an emulator. So this is again a univariate emulator. We're assuming that f of x is just a single output from our model. And the only difference here, of course, is that we could have multiple realizations of this output. And as always, we're splitting it into two parts. We've got our regression surface, our global part, which is going to be some basis functions multiplied by some regression coefficients, and that's going to try and capture the large scale behavior across the whole space. And we're going to have some local wiggly bits, and this we decompose into the actual u of x term that was in Ian's talks, and this nugget term, which was the extra bit due to inactive variables. And I'll talk about inactives in a little bit. But crucially, all of this chunk is effectively dealing with any local deviation away from our global surface. And again, as with all of the stuff we've talked about, this u of x, we give it some sort of structure. We need to give it a covariance structure in order to figure out how much a point has an impact on its neighboring points. Typically, if we assume the model to be quite smooth, to be differentiable, etc., we might choose something like an exponential squared correlation structure. Within the package, there are a few different options. You can choose Matern correlation, gamma exponentials, power exponentials. I think there are a few floating around, depending on how differentiable we feel the thing is, and you can always set it up to use those. And in Emulator from Data, I'll kind of discuss that a little bit. The crucial point here, though, is, well, we kind of said yesterday, we've got this sort of structure, we've got two hyperparameters in here. If we assume that we've chosen our correlation structure, we still have to think about what this sigma is and what this theta is. And we kind of said these were sort of like the overall uncertainty of our model and the correlation length for our correlation structure. Well, the correlation length in some sense hasn't changed. We would still expect parameter-wise sort of neighborhood relations to follow roughly the same structure. But crucially at this stage, we don't expect the variance across the space to be the same. So particularly when we think about the plot that Ian showed of the Bequano runs, we saw there was a difference in levels of stochasticity across the space. And if we were to just plonk a standard sigma value corresponding to potentially the largest spread, we'd end up really underrepresenting or underserving some of the more accurate or some of the less stochastic points. But similarly, if we would just take the smallest one, well, we'd end up missing out on quite a lot of stuff. So the only real sensible option here for that sort of model where we have that heteroscedasticity across the space is to start treating this sigma as being something that isn't constant. And that's kind of where this stochastic emulation stuff comes in. So from a functional point of view, from using the code point of view, actually, writing the code is relatively straightforward. We're still going to use this emulator from data function. It's still going to take some training data. It's going to take the names of the outputs that we want to emulate. It's going to take the ranges, which are going to be the input parameters as a named list, along with their lower and their upper bounds. And the only thing that's really changed is that we now have this other argument, which is emulator type, and we set it to variance. So all this is doing is telling the function that we are dealing with variance emulators. Incidentally, if you give it some data that has this repetition structure, so if it has multiple different results for the same parameter set, it will kind of flap a little bit and give you a warning and say, did you mean to do variance emulation? Because you've got repetitions in this data frame and not sure what to do with that if I'm doing this deterministically. So the safest thing usually is just to make sure we're clear about what we're doing here by setting this. So what does it do that's any different from the deterministic case? Well, it's going to take all of the runs, it's going to partition them out in terms of where the input parameter value is, and it's going to do a lot of stuff for making estimates of second order quantities and fourth order quantities. The reason for this is that it's going to try and train emulators to the variance surface, and it's going to use those as, in some sense, informed priors for the uncertainty on the mean surface. So we start to get this hierarchical system where we know we need to model the stochasticity. Well, how can we model the stochasticity? Well, we're in a modeling framework already. We've spent all of our time modeling outputs, so let's just treat the stochasticity as an output in its own right. We're going to have one of those for each output. So we're going to have a set of 10, 12, however many outputs we have, variance emulators, which themselves are going to give predictions about the stochasticity of the space, because that's kind of what an emulator does, right? So we can train these up, we give it its data, we adjust it, we make predictions across the whole space, and we can use that to inform how we create our mean emulators. And then what we end up with is a mean emulator that has its own uncertainty because it's predicting the mean surface, but it also knows about how stochastic the model is at every parameter set. And of course, those variance emulators come with uncertainties, which we have to deal with in their own little way. So we start out with our training data set, we split it up, we work out all these summary statistics in some sense. We use the variance data to train a variance emulator. They sit in their own little thing. Frequently, we probably wouldn't need to use them in any sense that matters. It's very rare that with a model, you'd have observational data that corresponds to how stochastic the model is. There are some cases, particularly in stuff like systems biology, where you do have that information, and actually you can treat these variance emulators as part of the history match. So you could have targets about how stochastic you expect the model to be, and you could use those in the implausibility measure. But typically these just live here just in case in some sense, and it gives us a way to analyze the space and to actually get a feel for what's going on with the model. The important bit is, well, once these are done, we build the emulators for the mean of each output. And this is kind of the default behavior. I think as Danny and Ian have mentioned, the idea of matching to realizations is a bit more complicated. It can be done in this manner, but it's a little bit trickier, and I don't think it's something that's within the scope of what we're going to discuss today, but I'd be more than happy to kind of give a brief summary at the end of the session. But crucially, we end up getting these emulators. They're trained in much the same way, and these are put into their own little list. And the output of this thing, unlike yesterday where it was a list where each element was an emulator, now we return a list where we have two elements, one of which is labeled variance and one of which is labeled expectation. And within each of those, we have emulators for each output. The reason we're setting this as expectation when we're referring to them as mean emulators is just to make sure we don't fall foul of overwriting or misusing one of the built-in R functions. So that's what we have. So we can take our data, we can run emulator from data on it, we can give it all the training runs, we can give it output names, ranges, it chugs away, and it will chuck out a sort of pair of sets of emulators. There is a crucial point here, which I don't know if is mentioned, but it's worth mentioning, which is one of the reasons that we give it the raw data is that there is no need to do the same number of repetitions at each point. So if you have parts of the parameter space that are very stochastic or very slow, so if you have particularly corners of parameter space where transmission rates, for example, are very high, your model is going to take longer to run in those parts of parameter space, and maybe you're not going to have the computational time to do a full 25 repetitions, maybe you can only do 5 repetitions. Conversely, maybe there are parts of the parameter space where nothing is happening, and we can do a ton of repetitions there to really pin down the variability. That's fine. We just do as many runs as we can at as many points as we can and stick them into here. And the variance emulators and the mean emulator that come from it will be aware of how many repetitions they've got at each point, and they'll be able to make the appropriate statements about the uncertainty. So all of that is kind of folded in and works behind the scenes to make sure that this takes into account the number of repetitions that we can do at each point. And this is something that Ian alluded to when he was talking about emulating the true mean. The idea is that we know that our data is not equal to the true mean, but it might be representative of it under certain assumptions. Cool. Okay, so you end up with your emulators, and again, we can start to do all the things we were doing yesterday. So one of the things we did yesterday was say, well, how do our variables affect our outputs? And we can start plotting which variables are active for certain outputs, which are not active, and which ones have been most informative. So for instance, if we look at the plot actives on the variance in particular, so this is looking at the variance emulators and which are most influencing the stochasticity of the model, we can see very quickly some of them are having very little effect. The beta and the mu, the birth and the death rates aren't really doing much. The first transmission parameter is doing a lot, which is kind of, we'd expect that if we have high first initial transmission, we're going to get a lot of variability later on. And interestingly, we have the gamma and the epsilon parameters also kind of weighing in quite a lot of the outputs. Just to quickly address one of the questions that I think was asked quite a bit earlier, the active variables question is a very interesting one. So when emulator from data is running, the first thing it tries to do is build up that regression surface, that first term we talked about here, the GTX transpose, etc., etc. it will try to build in as many terms as it can within reason. So something, if you think about how, if you've worked with LM in R and working with like stepwise add, stepwise delete, it's trying to do something like that on a rough sort of BIC criteria to get a good set of basis functions that aren't kind of overfitting. So that gives the first indication. If we build up that regression surface, we can look at it and say, well, which parameters are actually contributing to this and which are contributing to it in a meaningful fashion. So that gives us a way to start building up those active variables. Now, generally speaking, if we're building this using the default emulator from data, it will try to build a quadratic surface. So once you've got that set of initial linear active variables, so we build some nice linear model, we do all of our bits and pieces to make sure that the terms are actually reasonable. We look at them, we say, oh, well, we've seen that beta 1, epsilon, alpha, and gamma are in here. When we build up the quadratic part of that, we will start to add in the cross terms, add in the quadratic terms. And again, we will look at them to make sure that they're actually having a meaningful influence on the outputs. And then we do some final pruning to make sure that the proportion of variance explained by each individual term is sensible. Once we've got that, the active variables are kind of clear. If we have a term living in the model that has that parameter in, so either in a linear fashion, in a quadratic fashion, or in a cross terms fashion, we treat that as being active for this output. If it doesn't live in there, then naturally it's inactive. There is a certain question about whether, if it's in a cross term, but it doesn't exist as a linear or a quadratic part, should we be including it as an active variable? I'm not sure. I think it's an interesting question. I think for safety's sake, we tend to treat those kind of orphaned cross terms as being active variables, but I'm open to any convincing discussions about why that might not be the best thing to do. But that's kind of the rough idea of how we build up active variables. So similarly, for the expectation, we can plot the actives. And again, well, we see there's a lot more active variables here, which is not necessarily surprising. The output surface is probably going to be more dependent in general for a lot of these models on the inputs than the variance surfaces like the stochasticity. And we see there's a lot going on here. There are a lot of bits and pieces. Certainly the beta variables and our alphas and gammas and epsilons, just as in the variance surface, are having quite a large impact. There is also another function in the package which is called effect strength, which gives us a bit of a deeper dive into this, so we can get it to give out a grid plot just like this, but where each one is colored with how much of an effect that particular parameter is having for that output. So effect underscore strength will give you something very similar to this, where each color is darker if it is more strong and lighter if it is less strong. If there is no impact, it's pure white. And I think blue is positive and red is negative or something similar. So we can dig deeper into the active variables and the regression terms and their coefficients and figure out which parameters are having the biggest impact, which can be quite useful for kind of diagnosing models. As with yesterday, we still have all of the other plots. So in particular, we spoke a lot yesterday about emulator plot, which is our go-to way of plotting out the information in slices of our region. And this can, hopefully give us some indication of what's going on without having to run loads of model runs. We can use the emulator predictions as a surrogate. And it has the same sort of form here. We can give it any of our emulators. In fact, we can give it sets of our emulators, and we can tell it which parameters we want to slice along. So here we're plotting with respect to epsilon and alpha, and all the other ones are in principle assumed to take their mid-range values, but actually we can also specify them with this fixed vowels argument, which again we discussed yesterday. Here what we're doing is we're trying to plot a slice in epsilon alpha where all of the other parameters are fixed at the value that is set in the first training point. So if you look at this here, we've got all training. Well, we want the first row corresponding to our first training point. We want to take the names of our parameters, except for the 6th and the 7th, which of course is epsilon and alpha. So this is setting all of the other parameters at the values of the first parameter set we've put into the model. And the reason we're doing this here is just to highlight something quite important. So what we're plotting here is not the expectation of this, we're plotting the variance of this. So again, as yesterday, there are a few different things we can plot using emulator plot. One of them is the variance of the emulator, this uncertainty. And what we're going to also do, because this is a ggplot object, we can always add more things to it. We're going to also plot a point at the very training point. And that's that little black dot there that we can see. And we see kind of the structure we'd expect. we know that as we move further away from a training point, we expect to get less certain about the predictions. That's kind of naturally the sort of case. These emulators, if you think about the plots that Ian showed, as they move away from training points, they become further and further away. Those lines moved further and further away from the prediction. So that's kind of what we get here. We've got a training point, we've got the blues and the purples corresponding to low variance, and we've got the yellows corresponding to high variance, particularly at the corners. Now, one thing that is important to note is that if we look at the scale in particular, and this again in sort of analogy with the plots that Ian was showing, when we had those purple dots in his plots for the one-dimensional examples, we saw that the red lines, the uncertainties, kind of dipped right the way down and touched at that point. The idea is that at a training point, the emulators are certain about their predictions. Now, there seems to be a contradiction here, because if we look at our scale, well, it never goes lower than 41. And that's even at that point where we know there is a training point. We have plotted this that the training point is absolutely on the slice, and yet we're not getting zero variance. And the reason for that is because we're dealing with a stochastic system, because we haven't seen the true mean. Even if we have a training point corresponding to a set of repetitions at that point of the model, that is not perfect information. That is not information about the true mean that we're trying to emulate. So naturally, there is going to be some residual uncertainty, which corresponds to the underlying stochasticity of the model. So what we will see a lot of the time with these is that even at training points, we're never going to get down to zero uncertainty. We're never going to get to zero variance, simply because unless we see the true mean, which we're not going to be able to see unless we do infinitely many runs of the model, we can't have perfect information, and therefore we're not going to get this shrinking down to zero thing. So this is an important point just to highlight. It's not a bug of the package. It is actually representing a very crucial underlying mathematical concept. But that said, all of these things are all built in exactly the same way. So once we've built these emulators, we can do all of our bits and pieces. We can plot the active variables. We can plot effect strength, for example. We can plot the expectations, the variances. If you were here yesterday, of course, yes, we can change this to imp for the implausibilities and include the targets, and that is something that we'll discuss shortly. So all of these things, we've tried to make it as similar as possible to the deterministic case. And we will hopefully see that again when we talk about bimodality a bit later on. The functions should be as similar as indistinguishable from the point of view of using it. It's just that we have to be a little bit careful about how we interpret it when we actually get it out and how the differences sort of manifest themselves. So I will stop talking for 5 minutes. I'll give you the chance to play with training these emulators. Again, like we pointed out yesterday, because of the vagaries of R, even when you set a random seed in R, depending on your architecture, it will give you different results. This is even more the case when you're dealing with a stochastic system. So you might see that your active variables are slightly different, your plots are slightly different. Maybe you get ever so slightly different behaviors, but all of that is just coming from the sort of randomness of running the stochastic model at a randomly chosen set of points from the LHS.